Today, we are going to discuss two very important topics, and these two topics are NZ curves, NZ curve, and the another one is the binding energy. Binding energy. Binding energy. When I say it's a nuclear binding energy. Okay. So first, Uh, we'll discuss the NZ curve and then we'll go for the nuclear binding energy. So let us discuss what is NZ curve. We know that there are nuclei like carbon, oxygen, iron, calcium, which are stable, and there are nuclei which are not stable. So uh, we have stable nuclei and we have unstable nuclei. Okay, so unstable means these are maybe radioactive nuclei. Okay, so these are basically unstable nuclei. They're basically radioactive nuclei, and stable nuclei means they are remaining same throughout their life structure. So these unstable nuclei basically they constantly decaying into another radioactive nuclei. Like if A is some radioactive nuclei, it decays to some B and then to C and then to D and so on, unless and until finally they the product is a stable one. So this is what happens with the radioactive nuclei. They as soon as they come into existence, they start to decay. If this is the radioactive nuclei, they start to decay and they becomes some other product B, some other nuclei C and D, and they stop unless and until their the product is stable. For example, you know that carbon 12, this carbon 12 6, in which we have six protons, and we have six neutrons. Okay, so this is a stable nucleus, but an isotope of the carbon, isotope means the proton number is same, the neutron number is different, but an isotopes of the carbon, which is this is stable one. But if we say this is 14 carbon 6, this is an isotopes of the carbon. This is having a 6 proton and 8 neutrons. Okay, but this is unstable. This is unstable. So what happens when with 14 carbon 6, it is unstable, and the moment it is created in any nuclear reaction, it decays into it decays into 14 nitrogen 7. So this is 7 proton. Sorry, this is having 7 proton and 7 neutron, and it becomes stable. Okay, through a process which is known as the beta decay. The process in which the 14 carbon 6, it does a beta decay process. We will talk about the beta decay, and then through this process it becomes 47. So this is unstable and this becomes stable. Similarly, you know that uranium isotope, that is 238 uranium 92, we have 92 protons and 146 neutrons. If we uh, uh, this is my A and this is my Z, so A minus Z gives you this number of protons. So it is a radioactive. This is unstable. This is unstable. Okay, and it does an alpha decay process, and then it becomes 234 thorium 90. We have 90 protons and 144 neutron. This is stable one. Okay. So now you know that when we talk about the nuclei, there are stable nuclei, there are unstable nuclei, which you know as a radioactive nuclei, and then these radioactive nuclei, the moment they came into existence, they decay via certain process, and they keep on decaying unless and until the final product becomes unstable. Okay, so the question arises that why why nuclei nuclei with some combinations of neutrons and protons are more stable than others. Okay, so the combination of 6 proton and 6 neutron, which gives rise to the 12 carbon 6, is a stable one, but the combination of the 6 proton and 8 neutron, which is 14 carbon 6, is unstable. Why it is so? Similarly, if we have 92 proton and 146 neutron, it gives rise to a uranium isotope of this is unstable, but when we do combine 90 protons and 144 neutron, it is more stable than 288 uranium atom. Why it is so? So one way to answer this is to understand NZ curve. One way to answer this is the NZ curve. We can understand this through the NZ curves. So now we are going to discuss the NZ curve. So for that, let me first draw a rough sketch of the NZ curve. Okay. So this is my NZ curve. Uh, NZ curve. Okay. Uh, very rough sketch of NZ curve. On the x-axis, we have the proton number, and on the y-axis, we have neutron number n. So this is if you have nucleons, and if you plot the neutron numbers on the x-axis, on the y-axis, and proton number on the z-axis, this is how the curve look like. This dotted one is my n equal to z curve, and this red curve, this red curve is known as the line of stability. The line of stability. Okay, so what these two curves signify is that uh, if any nuclei is falling on uh, the n is equal to z curve, then it means that those nuclei are going to have e equal number of neutrons and equal number of protons. For example, if we have 12 carbon 6 nucleus, then we have 6 protons and we have 6 neutrons. So if we look for 6 proton and 6 neutron, number of z and number of n are equal, so this 12 carbon 6 nuclei are going to land on this n is equal to z curve. Similarly, if we see 14 nitrogen 7, so we have 7 proton and 7 neutrons. This is also going to be on the n is equal to z curve. So these are all stable nuclei. So because in the known scenario, but uh, not all combination of, because we know that the point is, let me write it, not all combinations of protons and neutrons gives us a stable nucleus. This we know that if we keep on connecting number of protons and neutrons and getting it together, then it's not necessary that every combination of proton and neutron is going to give us a stable nucleus like 12 carbon, 14 nitrogen, 14, or say 40 calcium, 20 sort of thing. In general, what happens that for light mass nuclei, in light mass nuclei, when I say light mass nuclei, then I mean to say that A is less than 20. So A is number of neutron plus number of protons. So in general, the light mass nuclei, if you look into that, that means the number of proton and neutron has to be 20. If you look into um, uh, number of proton neutron is 10. If you draw a line, if we have a number of neutron is 10, then it is cutting here, and the number of proton is also 10. So at this position, so such system is lying close to the n is equal to z line, as well as uh, on the line of stability. They are basically lying on these two. And similarly, if we look for neutron number 20, if you draw the line here, then it is cutting, and if you draw n is equal to 20 here, then I can see that it's also lying as well as on near to line of stability, as well as on the line n is equal to z curve, because both have a number of proton and neutrons different. So but for heavier mass, for heavier mass nuclei, say when I have A greater than 20, neutron neutron number neutron number exceed exceeds proton numbers in nuclei. So when we talk about heavier mass, whose mass number A is greater than 20, then the neutron number of neutron in the nuclei exceeds the number of protons in the nuclei. You can see here that uh, if I keep on increasing the neutron number, for case if you consider if you consider 40 calcium 20, 40 calcium 20, so if we have 20 protons and 20 neutrons, this is as you can see that this is very near to n is equal to z, as well as to the line of stability. And the next, if we consider 56 iron 26, this has 26 proton and 30 neutrons. If we consider the 30 neutrons, if we draw the line, so it is 30 neutrons, and then if we come across to the z number, this is here. So n here is like sorry, z here is, z here is 26. So now you can see that for this iron isotope, this iron isotope is the most stable isotope of iron. So in this case, you can see that we have less number of proton and greater number of neutron to this system to be stable. So in the similar fashion, if we go on increasing the number of protons, then you can see that the nucleus to be stable, mm, a nucleus must have more and more number of neutrons, because you can see, if you see the line of stability, those nuclei which sits on this line of stability, this red solid curve, they are going to be more stable as compared to their different isotopes. So if nature has chosen that if a system has to be most stable, then if we increase the number of proton in that system, then the number of neutron has to be more than the number of proton in that system to be more stable as compared to the different neighborhood nuclei or the isotopes. So uh, this is as you can see that this is very much evident from the shape of the NZ curve, that is, which we know that at the line of stability. So around the line of stability, we have more number of nucleons, like these nucleons. These are more number of nucleons exist near the line of stability. Around the line of stability, these are more number of nucleon. So the if you choose this nucleon will be less stable as compared to the nucleon, the isotope of this particular nucleon, which is existing on the line of stability. So if we draw a straight line here, then this will give us the isotopes of the same nuclei. So this is the isotope of the same nuclei, this is isotope of the same nuclei, but the isotope which will be on the line of stability, which will be more stable as compared to this nuclei or this nuclei or this nuclei, which is the isotope of the same nuclei. And these lines are known as the drip lines. We will talk about the drip lines later on. This is known as the proton drip line, and this one is known as the neutron drip line. And all these nuclei which are in between this line of stability and the proton drip line are known as the beta plus emitters, and all those nuclei which are lying on the left side of the line of stability within the neutron drip line, they are known as the beta minus emitter. So these are very important vocabulary. What is a neutron decline? What is a proton decline? Beta minus emitter, beta plus emitter. Those nuclei which are on the right side of the line of stability, they are beta plus emitters. Those on the left side of the line of stability, they are known as the beta minus emitter. And the end of the boundary of the existence of these nuclei, beta plus or beta minus, are known as the respective proton decline and the neutron decline. We will talk about this decline later in the later stage. So this is what we have NZ curve. If you plot all the nuclei, their proton number on the x-axis, neutron number on the y-axis, and if you plot different nuclei, then you are going to get this red solid curve, the line of stability, and the many nuclei which are existing around the line of stability, in between line of stability and in the proton drip line. So the conclusion which the most important conclusion which has to which is there through this NZ curve is that system has to be stable. If a system is stable, then, or a nucleus is stable, then it has to have a more number of neutron as compared to the proton. So we have to discuss that what is the reason, that um, neutron number being greater as compared to the proton uh, for nuclei to be stable. So let us try to understand this. And what is the reason that neutrons are greater than number of protons? That a stable nucleus has greater number of neutrons as compared to proton. So to understand this, let us try to understand that. Let us consider that this is my nucleus look like, in which we have this is my this is my proton, and this is my neutron. So inside the nucleus, I have a number of proton and number of neutrons sitting there. So why these are sitting together in such a tiny space? So because we know that the radius of a typical nucleus is about this is about 10 to the power minus 15 meter, or 1 Fermi, of the 1 Fermi. So why within such a tiny space so much of protons and neutrons are sitting together? The answer is due to the strong nuclear force, which is the strongest force existing in the nature. So my question is that why these nucleons are sitting inside such a tiny space altogether. So the answer to this is that this is because of strong nuclear force. And this is the strongest force existing in nature. So because of this strong nuclear force, these nucleons are made to held together in such a tiny space, and this is the strongest force existing in nature. Let us first try to understand some of the properties of this nature, which will help us to understand that why we need more number of neutrons than proton to be a system to be stable. So the first property of this system is it is an attractive force. That means this force attracts proton neutrons together. Okay, and this is pretty obvious. Otherwise, if this force nature of this force has to be repulsive, then they are not sitting together in such a space. The second one is they're charge independent. The force is charge independent. What do I mean by the charge independent? You know that that proton is a positively charged. You know, proton has a charge of plus, charge of plus unit, and neutron has no charge. Okay, so because a proton is a charged particle, it is having a Coulomb repulsion force also, and this is neutron is a neutral particle. So proton are being um, affected by the Coulomb repulsion force also. But this strong nuclear force, whether it is a proton proton or a proton neutron, or we have a neutron neutron, it is working equally well between all these three, whether it is proton proton, whether it's a proton neutron, whether it's a neutron neutron. This far, the strength of this force is equal in if it is acting between proton proton or proton neutron or neutron neutron. It is not distinguishing that whether it is a proton or whether it is a neutron. So that's why it is a charge independent. The third property is that it is saturated in nature. Saturated in nature. What does it mean? It is a short range force. Short range force. So this is effective. Let me explain it. Effective uh, within a very short range, acting between the neighboring nuclei. Neighboring nucleons only. What does it mean? The force is saturated in nature. So uh, to understand this, uh, we can understand this like this, that because this is my nucleus and this is the boundary of my nucleus. These are the boundary of my nucleus, and the nucleus are neutrons and proton are sitting inside this. But what happens that if we choose this neutron here, and this proton is sitting here, or this neutron is sitting here on the other side of the system. So this, there is no this is not between these two, there is no nuclear force. Similarly, between these two, there is no nuclear force is acting, because the nuclear force is saturated. It acts between a very short distance. So what does it mean that if you draw a range, if you draw a range like this, like this, or say like this, then within this short range, then these nucleons are being interacted through the nuclear force between all these together. Similarly, these are being attracted towards nuclear force, or this this these are being attracted by nuclear force. But it is not happening that one neutron from this region is being attracted by the other neutron by this region. this is effectively attracted by this proton, because if we draw a region, this will be a small region, but it's not that this is being attracted by nuclear force with these neutrons. So if this neutron is sitting at this side and this is at this side, then they are not going affected by the strong nuclear force. But the proton, if you talk about the proton is sitting here and the proton is sitting here, they are being affected by the Coulomb repulsion force because they are charged, but they're still not affected by the strong nuclear force, because the strong nuclear force is acting for a very short range and they are just acting in the neighborhood of the different nucleons. That is what do I mean by this force is saturated in nature. So these three quantities, attractive in nature, they're charge independent, and the important one, that this is saturated in nature, they are responsible to give us the answer for the reason that why the number of neutrons are greater in number as compared to the number of proton for the most of the stable nuclei which exist in nature. So let us try to understand or answer based on these three forces, that how we can understand. So for that, let me let me I have this picture, this scenario. This is my nucleus, uh, in which I have a number of protons. I have not made it number of neutron here. So we know that since protons has charged particles. Okay, so we know that proton is charged particle. We have proton, and they have plus charge. Okay, so naturally they must be repelling each other. These all these proton are repelling each other. Okay, all these proton are repelling each other. So it has been found that if I have a nucleus in which uh, number of protons if greater than 10, if I have a system in which number of protons greater than 10, the nucleus does not remain stable. Because the repulsive force, Coulomb repulsive force, made these proton fly apart, and naturally we are not going to have a stable system. So but we know one thing, that if we have a proton system, if we have two proton, then they are being repelled by the Coulomb force, which I say this is Fc, and they are being attracted by the nuclear force, Fn. So when we have a proton greater than 10 in a system, we have that the Coulomb force dominates over the forces, the nuclear force which is acting between these proton, and the system is unstable. This is pretty obvious. So we need a system to be stable. So we need the nuclear force to be greater than the Coulomb force, and to do so we need more number of neutrons. We need greater number of neutrons as compared to protons. because nuclear force is charge independent and attractive in nature. So if I fill this, if I take the number of neutrons, which are these green one, if I fill these system with number of neutrons, these are my neutrons, then what will happen? Apart being these neutrons are being getting their Coulomb repulsion and flying from each other apart, and if we put the neutrons in here in between them, then what will happen? If we consider this region, let me consider this region, or let me consider this region uh, first. Let me consider this region. So what is happening here? These three protons are under Coulomb repulsion, but all these three protons, and all these like 1, 2, 3, and 4, all these 5, 6, 7 nucleons are being under strong nuclear force. This is attracting with due to the strong nuclear force. This is attracting with a strong nuclear force. This is attracting with a strong nuclear force. This and this, they are themselves attracting these system. This is also attracting with the nuclear force. These are so within this vicinity, the nuclear force now dominates. The nuclear force dominate to the Coulomb force because of these protons, and the system becomes try to become stable. So that is why if we have a more number of protons, and the Coulomb, when the Coulomb force becomes more dominating than the nuclear force, and then in order to balance the system, we need that the nuclear force has to be greater as compared to the Coulomb force. So Coulomb force, nuclear force will be greater because we have more number of neutrons. If we add on more number of protons, the Coulomb repulsion force will be more, so the system will not be stable. System will always be having a Coulomb force dominating over the nuclear force. Uh, until we put a more number of neutrons, because we know that the nuclear force is charge independent. It doesn't differentiate what is proton and what is neutron. So the number of attraction in that region between the nucleons increases, and this overpowers the number of Coulomb repulsion within that short region. And that's why the system as a overall becomes stable. So that is why you see that the line of stability move towards the y-axis, which is giving you that the system to be stable, more and more number of neutrons has to be there, which is chosen by the nature. In nature, we have whatever we have four types of system. Uh, I can write it down. This first system is like even system, even, which is right as even. That means Z number is even and N number is even. For example, you can see that to a carbon 6, we have even number of proton, even number of neutrons, like this. So such stable even systems are almost of 60% of is existing in the nature. Then we have even odd system, which is represented as EO, in which we have Z even and N number odd. And then we have odd even system, we have OE, we have Z odd, and n even. And these are existence of these are equally numbered. And then we are left with the last one, which is odd odd. This is OO, in which we have Z odd and we have N odd. These are very few in numbers. Around 7 to 8 nuclei exist in nature, which are stable in odd odd. Like you have deuterium, 6 lithium 3, you have 10 beryllium 5, 14 nitrogen 7, 180 Ta 73. The very few nuclei which are odd in numbers. This number of proton is 7, number of neutron is 7. So uh, this is all about that, what is NZ curve, and why. The conclusion from the NZ curve was that if a system to be stable, we need more number of neutron as compared to the more number of proton, because and that is evident from the curve. And you know that why we need more number of neutron to as compared to the proton to a system to be stable. And but the story does not end here. In case of very large nuclei, what happens, like if we have a nuclei which has a mass number greater than 200, that means the number of nucleons is 200. Then what happens, the proton the repulsive Coulomb force, because the proton is perceived everywhere inside the nucleus, because the size of the nucleus is so large, so the Coulomb repulsion is appreciable everywhere. So in that case, even though the number of neutrons are much greater than the number of protons, uh, but but uh, but the system does not remain stable, because the Coulomb force, because is not short range. It is like, we know that, like if we have two masses, gravitational force anywhere in the universe, if m1 m2 anywhere in the universe, they are separated by the r is infinity, they are still attracting each other. Similarly, if we have a electron and positron and they are anywhere, if r is even infinity, they are attracting each other. But it's not with the nuclear force. So if the number of proton is there and the system is very large, so the proton is the Coulomb repulsion is appreciable everywhere inside the system. And so there is still a limitation that we can put on more number of neutrons in the system. So for large system, the nucleus is still not stable, and it becomes unstable. So what happens in such cases? Uh, in such cases, the limiting start with like 209 bismuth, which is having an 83 protons. So in which you have 83 protons, and then you can have 209 minus 83. So this will be 6, and this is 12, 126. Okay, so 126 neutrons is there. So even 83 protons are there and 126 neutrons are there. This system is unstable, because the presence of more number of neutron is still not going to overcome the repulsive Coulomb force, which is acting between the 83 protons. So which is the heaviest stable nuclei? uh, Still, sorry, this is this is the heaviest stable nuclei. So if we have Z greater than 83 and A greater than 209, so then in this case we are not going to have a stable system, then we are going to have unstable system. System means the nuclei, what we are talking about is the nuclei. So what happened for such cases? In such cases, the unstable system, the moment system which are came into existence, which are having a Z number greater than 83 and A greater than 209, when they transform, like if I have, say, if I have system which is of a greater than 209 and z greater than 83 is being created, then what happens? They decay. They decay via an alpha decay process, in which we have uh, the alpha decay process is known as this, and this we have 4 helium 2. So this is alpha particle, this is the daughter nucleus, and this is the parent nucleus. So this system, this nucleus, which is having a greater than 209 and z greater than 83, it is created. But beside having more number of neutron than proton, it is not stable. And to being stable, it goes under a decay process which is known as the alpha decay, in which we have a new system nucleus found, in which we have the a number being decreased by number of 4 and z is decreased by number of 2, and then we have the 4 which is decreased, and this is, and we have along with alpha particle coming out in this process, which is 4 helium 2. So this is a kind of nuclear decay process. So since an alpha particle consists of this is my alpha particle consists of 2 protons and 2 neutrons, and alpha decay reduces the z number by 2, and the n by original nucleus by 2, and the overall a by 4. And this leads to the balancing between the repulsive force between the protons and the attractive nuclear force between all the nucleons, protons and neutrons. And the final nucleus becomes, this is this nucleus was unstable, and this becomes stable. So whatever number of alpha particle decay it has, this system has to do, it goes on this, and then the system becomes unstable. If after doing this alpha decay, this system is still unstable, then it goes more number of alpha particle. If it, then after then also this is not being stable, then it keep on decaying through via different process, and the another process is negative beta decay. So I put a negative sign here. What happens in which a neutron of the system becomes a proton of plus charge, and then an electron comes out, and then we have an neutrino. This will have anti neutrino, and then we have a positive beta decay, in which a proton which becomes a neutron, which have a zero charge, neutral, and a positron and a neutrino. If I put a bar over a neutrino, it becomes antiparticle. Just like we have an electron and then have a positron. These are the antiparticle. Electron is a particle. This is antiparticle. Similarly, if I have a neutrino and I put a bar over here, it becomes an antineutrino. So using this alpha decay process, negative beta decay and positive beta decay, so doing all these decay process, a stable nucleus in which we have a more number of neutrons than protons, they try to become stable, and finally it becomes stable using alpha decay or negative beta decay or positive beta decay. Let me draw a curve to understand that how all these nuclear decay helps an unstable nucleus to become stable and move towards the line of stability. So if I say is my number of say this is my Z, and this is my neutron number n on this side, and we have number of proton on this side. So if I have my line of stability, which is moving towards number of n, so what happens when we do alpha decay, in alpha decay we know n decreases by 2 and z decreases by 2. So uh, so what will happen that to come to this line, so if a system is coming to this line, so this system, if this is here, so it will decrease here, and it will let me, so it will decrease in neutron number by 2, and it will decrease in proton number by 2, and then final product will be that it will reach to this line of stability. So if this is my system, this does an alpha decay, and this is z minus 2, this is n minus 2, sorry, this line gives you n minus 2, and this line gives you z minus 2, and then finally it reaches to the line of stability. Okay, similarly this is my stability curve. And if we do the negative beta decay, what happened in negative beta decay, we have a neutron is going into a proton. Okay, so a neutron, less in neutron, a neutron number will be less by 1, and proton number will be increased by 1. So so what will happen, so if I have a system, if I have a nucleus here, so say if I have a nucleus here, so proton number means negative beta decay means that will be a beta minus. So means what is happening in negative beta decay, that I need more protons. Okay, we have more neutrons, so I need more protons. Neutron becomes a proton, so so I need a neutron to be minus, so neutron will be this will be n minus 1, and this proton will be uh, increase, like I am moving towards here, so this is z plus 1, and then finally what we have is a system which was here comes to a system which was here comes to, it does a neutron going to proton plus electron plus antineutrino, and the system which was not on the line of stability here, in this case it was here in this case, and then by doing n minus 1 and z plus 1, that is negative beta decay, it comes to the line of stability. Similarly, the system which was here, by doing an alpha decay, decreasing its number of neutrons by 2 and number of proton by 2, it finally comes to the line of stability and becomes a stable system. Similarly, for if I say for positive beta decay, in which a proton is being transformed into neutron, so that means in the system I am decreasing the number of proton and increasing the number of neutron. So this will happen, that increasing the number of protons means that um, system will be here somewhere, like let me just say system is here, so I am decreasing the number of proton and increasing the number of neutrons. Okay, and then finally the system from here goes to here. So what is happening, that I am this z minus 1, and here is n plus 1, and then the system goes to the line of stability here. This is beta plus emission, and this was beta minus emission. So this is how this decay process helps an unstable system which is large enough, and the more number of neutron is not capable of holding the system to be stable, it start to, the moment it creates in certain reaction, it start to decay via alpha decay, negative beta decay, or positive beta decay, and it tries to come through such decay process towards on the line of stability to become unstable. So this is how we do this. Another important point uh, which I want to discuss here is the nuclear drip line. So which I had let me come to the previous slide. Let me come to the previous slide. How it will go to previous slide. Uh, so another important point which I want to discuss here is the neutron nuclear drip line. So there are two type of drip line. One is as I had told you, this is my proton drip line. These lines, these drip lines, these are the proton drip line, which is a beta emitter line, and the another one is, this is my neutron drip line. So these are the two sides of the line of the stability. This is my line of stability, and these are the two sides of the line of stability around which we have the nucleons sitting around. So these nuclei are having more number of protons than neutrons, and these are more number of neutrons than protons. So the nuclear drip line, let me see, we are talking about the nuclear drip lines. So one is proton drip line, and the another one is the neutron drip line. The nuclear drip line is the boundary. Uh, the nuclear drip line is the boundary which limits uh, the region beyond which atomic nuclei are no longer stable. They spontaneously start to decay by the emission of a proton or neutron. So literally speaking, the nucleons from these unstable nuclei start to leak or drip out of the nucleus, hence giving rise to the term drip line. In this process, therefore, one can think of that finally the new nucleus ends up being on the line of stability. So what happens that if I have a nucleus in which I have a protons or I have neutrons, so what happens in such cases if you have a nuclei, such nuclei which is around this neutron drip line, that means the more number of neutron is there. So if this is my nuclei which is having a number of neutron more than the proton, But this is unstable because this is not on the line of stability. This is not on the line of stability. So this nucleus will try to come on the line of stability, and for doing so it will try to go through different process. So why it is known as the dripline nuclei, because it's like it's the end of you cannot add more number of neutrons or protons inside this nucleus. It is the limit. The moment it happens, like if the system is towards the neutron repline, so a neutron, basically a neutron will try to drip out of the system. It will try to leak out from the system. That is in keeping this, so that means this neutron becomes a this neutron try to becomes a proton, and along with this we will come an electron and an antineutrino. So this is as the beta minus decay. And by doing so, this system try to come to the new line of stability. Similarly, if this system is here towards the proton drip line, what will happen? The proton try to leak out. This is the limit. If the proton will try to leak out or drop out of the system. So in such cases, the proton is drip out of the system, and then this becomes a neutron and an positron, and then neutrino will come out. So this in this is for doing so, this nucleus will try to come to the line of stability. So this is what you need to know at this state of the system, that what is the neutron drip line and what is the proton drip line. So literally speaking, the nucleons from these unstable nuclei, which are at the neutron drip line, they start to leak or drift out the nucleons of their nucleus, and hence giving rise to the term drip line. In this process, therefore, the nucleus which were at the boundary or around the drip line, they try to come to the line of stability and becomes unstable. So now in the next lecture we'll try to discuss the nuclear binding energy.